Hello, this is your Lakshma Reddy sir. We are in chemical kinetics, right? Temperature dependence of the rate of a reaction. Temperature dependence of the rate of a reaction. That means how temperature is going to affect the rate of a reaction. Let's take the simple example N2O5. N2O5 decomposes. Okay, decomposes to you can say NO2 plus O2. This reaction is very fast, okay, at 50 degrees Celsius. Half of the amount will be completed in just 12 minutes. NCRT data this is, there is no need to remember, but you can see the difference. At 25 degrees Celsius, it takes around 5 hours, and at 0 degrees Celsius, it will be taking around 10 days. So as the temperature increases, you can see the rate of a reaction is increasing in general. Otherwise, you know this very well, potassium permanganate and oxalic acid reaction you are performing in your laboratory. Yes, yeah. Generally, we add there concentrated sulfuric acid beta. Otherwise, sulfuric acid dilute we add and we heat that one. If you are not heating, the reaction will be very slow. Okay. The decoloration of KMnO4 you can say, or the reaction will be very slow at low temperatures. And if you are heating the temperature, that means high temperatures, the reaction will be very fast. And what your teachers do is, instead of adding dilute H2SO4, they add concentrated sulfuric acid. Then obviously the reaction will be very fast. Okay, but actually you need to add dilute H2SO4 and you need to heat gently so that the reaction will be very fast. In order to avoid this time wastage, simply we add their concentrated sulfuric acid, which is not actually the process but can be done. Then we have an equation that is K is equals to A E minus EA by RT. Okay, now K we know that is rate constant, correct. A is known as Arrhenius factor. Arrhenius factor is also called frequency factor. Arrhenius factor or frequency factor, or you can call this as pre-exponential factor. Pre-exponential factor. And this is for a particular reaction, it is going to be very specific. It is a constant specific to a particular reaction. That means you can't say that like Avogadro's number, it is not constant, but it is a constant for a particular reaction. Or we know gas constant, terms I am explaining, and EA is activation energy. So we need one new term here. What is activation energy? We'll go to activation energy, don't worry. And activation energy generally given in joules per mole. K is rate constant, A is Arrhenius factor, E is the base, EA is the activation energy, or T is the temperature. So this equation is known as Arrhenius equation. Very, very, very important equation, you can say. Coming to the other important lines of this. When you take a simple reaction, H2 plus I2 gives rise to 2HI. You know how the reaction takes place? There will be a bond between H and H. There will be a bond between I and I. Now slowly this bond should break, and slowly iodine-iodine bond should break. At the same time, slowly this bond should form. So this is called activated complex, or you say intermediate. Through an intermediate it is going to happen, and then the bonds will break and it is going to form HI and HI. These are the products. According to Arrhenius, what he says is generally when a molecule, when the reacting molecules are reacting, it is going to form an intermediate, and later intermediate breaks up and converts into products. And intermediate is generally unstable. If it is stable, the further reaction won't take place. So it is going to be unstable and later turns into products. Here what you need is one simple graph. See here I am taking reaction coordinate. What is the meaning of reaction coordinate? Most of the times you will be saying reaction coordinate. Every time that will be mentioned. The reaction coordinate represents the profile of energy change. Represents profile of energy change. That's how the energy change takes place. Profile of energy change is given by reaction coordinate. Now see the graph. Okay, it is the energy of reactants. This is the energy of products. Correct. Energy of reactants is more than energy of products. So this is going to be an exothermic reaction. Thermodynamics, first year, class 11. Okay. Now you see, this is known as activated complex. Through activated complex only, the reactants are converted to products. They are not going directly like this. They have to pass through the activated complex. That means if you want to join IIT, if you are in Hyderabad, IIT is in Hyderabad only. Directly you can go and join. No, this is not possible. You have to clear the entrance. So this is like entrance examination, right? Activated complex. For that purpose, you need to prepare, and this is that energy required. Activation energy. Activation energy is the energy required for the molecules to reach the activated complex. Once the activated complex is reached, this is unstable and it immediately turns into the products. And formation of the activated complex is only the slow step. Breaking of the activated complex is the easy step. And the energy of reactants plus activation energy, this together is called threshold energy. Don't confuse with this term. Threshold energy is the sum of energy of reactants plus activation energy. Energy of reactants and activation energy sum is called threshold energy. The energy required to reach the activated complex by the reactant molecules is called activation energy. If it is a reversible reaction, you can say this is also activation energy. Okay, now for backward reaction, now we are discussing only forward reaction, so I am not taking you into that details. So this is the graph that you need. Okay, so compulsorily the reactant molecules must cross through the activated complex to turn into the products. Very, very simple theory it is. Then see one more theory. This you have studied in your class 11, states of matter. Do you remember this graph? Here I am taking the fraction of molecules. What fraction of molecules I am taking here? Ne by Nt. Ne means the number of molecules possessing activation energy. Nt is total number of molecules. And here I am taking kinetic energy. And this particular is known as highest fraction of molecules. So this energy is called most probable kinetic energy. This point we were discussing gaseous state as most probable velocity. So similarly, most probable kinetic energy. On y-axis fraction of molecules, on x-axis kinetic energy, and the graph will be like this. This is most probable kinetic energy, but this is not sufficient. Actually, the activation energy will be somewhere here. Okay, now so all the molecules are not the maximum molecules possessing. Very few molecules are only possessing the activation energy. This is the energy possessed by the maximum number of molecules. Maximum number of molecules energy is most probable energy, and here we are discussing about the activation energy. Activation energy will be here somewhere. Okay, now I'll give you that graph also. See this one. Fine. This is the graph we are taking at a temperature T1, you say. Now if you increase the temperature by around 10 degrees like that, we'll add here. See, in these two cases, area under the curve must be same. Remember, area under the curve must be same beta. And you see, this is the max. This is again same fraction of molecules. Fraction of molecules. And here we are taking kinetic energy. Done. Fraction of molecules is equal to Nt, E by Nt, right? N is activation energy containing molecules, Nt is total number of molecules. Here kinetic energy, and this is, yes, exactly, most probable kinetic energy. This is the kinetic, and this is the maximum number of molecules. So this particular part is called most probable kinetic energy. This we are not discussing now. We are going to discuss about this. Let's say this is the activation energy. This is the activation energy. That means the molecules must possess this much of energy. So after this, how many molecules are there, you see? Okay, now this is the part that we are going to show here with red color sign. This is the fraction of molecules which can be converted into products. These will be converted into products. The second graph what you have taken is at T1 plus 10 degrees Celsius. So you are increasing the temperature. Whenever temperature is increased, generally for every 10 degrees rise in temperature, rate constant will be doubled, sometimes tripled also. So in general doubled. Okay, that is only called temperature coefficient. Temperature coefficient is K T plus 10 degrees by K T degrees Celsius is equals to, in general, 2, sometimes 3 also. This is called temperature coefficient. Okay, now the ratio of rate constants differing by 10 degrees Celsius is generally equals to 2, sometimes equals to even 3 also. 2, 2.5, 2.6, anything is possible. Now you see the interesting point. After increasing the temperature by 10 degrees Celsius, now you see the area under this is the activation energy. Now you see this is the extra area, extra fraction of molecules which can be converted into products. Earlier only these many number of molecules were the red color area, you can see that only are converted into products, that fraction of molecules only converted into products. But now these many molecules can be converted, these many extra molecules can be converted into products by increasing just 10 degrees Celsius. Okay, that means when you are increasing the temperature by 10 degrees Celsius, the height of the curve decreased, it became little broadened, it shifted towards right, and number of molecules, fraction of molecules with more activation energy, more than activation energy is more increased, and they are converted into products. That means when you are increasing temperature, definitely the rate of reaction increases. And remember, in these two cases, the area under the curve must be constant, since total probability must be 1 at all times. Right, the area under the curve must be constant, since total probability must be 1 at all times. So this is about the graph that you need to know. Now 2-3 simple equations and we'll conclude this part. Ln K is equals to minus EA by RT plus ln A. This you can write from K is equals to AE to the power of minus EA by RT. On applying ln, you can get this one. This we will apply for two different temperatures. Ln K1 is equals to minus EA by RT1. Ln A, it won't change, but A is the Arrhenius factor, it is not changing. Ln K2 is equal to minus EA by RT2. Ln A. Now this is expression 1, this is expression 2, expression 2 minus 1. When you are subtracting this, you can get ln K2 minus ln K1 is equals to EA by RT1 minus EA by RT2. There is minus sign, you can notice. Minus EA by RT2, minus of minus EA by RT1 is nothing but EA by RT1 minus EA by RT2. Right? Ln K2 by K1 is equals to, from this you can take out EA by R. EA by R is taken common. So this is 1 by T1 minus 1 by T2. Or you can apply here log K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2. Or log K2 by K1 is equals to EA by 2.303 R T2 minus T1 by T1 T2. This is very important equation, and you need to remember this equation. For two different temperatures, rate constants can be calculated using this expression. Very important. You have to work on this. And one last line, we'll take up a graph and conclude this one. Ln K versus 1 by T, when you are taking, it is with negative slope. This intercept part is ln A, Arrhenius factor, and the slope is going to be negative, that is minus EA by R. Negative slope minus EA by R. Ln A is the intercept. Graph is between ln K and 1 by T. Right, this is your Lakshma sir. Thank you. Any doubts, you can contact me anytime. 890-446-7423 at your service.